What I do. Go on. Yeah. It's just salt free seasoning. Girl, oh my God, stop. It smells good. That's where. All right. Are you ready to continue the best topic in the world? Amazing. Of many things. Well, okay, so why is it important to analyze protein content, Ali? Because labeling. Thank you. Sorry. What else? Lookman. What's that? Quality control, for sure. What else? Health claims? Yes, if we want to do a health claim, we need to meet a certain requirements. And also testing functionality is based on protein content. Testing enzyme activity is based on protein content. Oh, and then another important one is protein fractionation and purification. I don't think we talked about that last time, but you know, in industry, they sell protein concentrates and protein isolates. So there is a minimum protein content for the ingredient to be labeled as protein concentrate and for the ingredient to be labeled as a protein isolate. For example, there are rules for soy protein specifically. Anything under 90% protein cannot be called protein isolate for soy. However, for all other plant proteins, 80% and above can be considered a protein isolate. So there are rules and regulations for labeling ingredients as a concentrate or an isolate. So that's why it's important from an industry side of things to get the protein content. From the research side of things, when we are discovering new protein sources, crops, we need to figure out ways to get the protein out. And then we need to determine the efficiency of extraction. So we monitor protein content. Okay. There are so many methods to measure protein content. The official methods of analysis are Kaldal and Dumas, which we will do in the lab. There are other methods of analysis. Oh, there's a ring. Everybody missed a ring. That's not part of the lecture. Okay. So for quick quality, no, you should sit over there. They mix it up on you today, so continue. All right. So infrared spectroscopy for quick quality control method of analysis for protein. And then there are a bunch of research methods. We're going to talk about a couple in the lab. You're going to do Bradford analysis, Dumas, and Kaldal. Okay, so let's talk about Kaldal, my favorite protein analysis method. Now you're not going to believe that it's my favorite, but it's truly my favorite, and I have a story later. Okay, so Kaldal analysis is based on measuring nitrogen content, but it's a series of reactions. So when I tell you what are the main steps in Kaldal, you want to know digestion, neutralization, and distillation is one step. So you want to know, you want to say digestion, neutralization / distillation, and finally titration. So these are the 3 steps in Kaldal, and you will learn those in lab next week. And then after we determine nitrogen content, we need to convert it to protein content. Every protein type has a percentage of nitrogen in it. Why do you think the percentage of nitrogen is not the same for all proteins? Why do you think? Those of you in food chemistry, yeah. Very good, that's the key word. Proteins differ in amino acids, but what amino acids have more nitrogen than other amino acids? Do you know that? They are polar, but there is specific component in the R chain that makes them have more nitrogen. Basic amino acids. They have amine groups in their R chain. You know, every amino acid has an amine group and a carboxyl group. Basic amino acids have in the R chain, they have an additional 1 or 2 or 3 amine groups. So these are, do you remember your basic amino acid? Yes, what are they? Huh?
Wait, what? Wait, what was the question? I'm sorry.
What are the basic amino acids?
Glutamine, glycine. Am I even right? Glycine.
Huh? Good try. A for effort, huh?
Glycine.
Lysine, that's one. Arginine and histidine. Glutamic acid. Glutamine, it can convert to glutamic acid, and their natural glutamic acid, these are acidic. Glutamic acid, aspartic acid, these are acidic. So the basic amino acids in particular have more nitrogen in them. And proteins that have more of these proportion of these amino acids will have more nitrogen in them, okay, than other proteins that have less of these amino acids. So that's why different proteins will have different conversion factors. So you will be working in the lab with the cheese, the baby cereal, the almond. Each one of them will have a different conversion factor because they have a different percent nitrogen. So to convert nitrogen to protein, we have to multiply by the conversion factor, which is 100 over 16. 16 is an average of percent nitrogen. So this is 6.25 is the kind of commonly used conversion factor. If we don't know the conversion factor of a protein, we just use 6.25, which gives you, which is 100 over 16, which 16 is the average percent of nitrogen in protein. But there are proteins that have 17%, 18%, or 12%, so that conversion factor will be different. Okay. So it is a crude method of analysis. Can you tell me why it's crude? We talked about crude analyses, approximate methods of analysis. Why is protein analysis by Keldar is crude? Not accurate, not like you're exactly calculating protein content. There are other sources of nitrogen than the protein. Nucleic acids have nitrogen, vitamins have nitrogen, so urea has nitrogen. So there are different sources of nitrogen in your protein or in your food sample that is not necessarily coming from protein. So oftentimes the crude protein content is slightly higher than the actual protein content. Okay, so very good. Let's talk business or chemistry. All right, so the first step is we want to digest the food so that we can get rid of all organic matter except the amine group. So what we do here is we digest the food with the concentrated sulfuric acid, heat, and we add catalyst. The catalyst specifically is added to raise the boiling point of sulfuric acid. So to prevent early evaporation of the acid, so to enhance the efficiency of digestion. Okay, so we put sulfuric acid, heat, and then what happens, we start having burning of the food and fumes coming out. And these fumes have CO2, H2O, SO2. Okay, so these are all fumes that get exhausted out of the cell. Now, the amine groups in your proteins or other sources of amine groups will be fixed by the sulfate. So we produce ammonium sulfate. Now you'll see that I put everything in red that we are following the amine group. So we're after determining the nitrogen. So everything that has the amine group in it is in red. So the first step is digesting everything and fixing, that's the word, fixing the amine group as ammonium sulfate. So that's the first step. Now our ammonium sulfate is fixed. You'll see in the lab after digestion, you will have a clear kind of solution that looks a little bluish because of the copper catalyst. And your H2SO4 reacted with the amine group to give you ammonium sulfate, which will be dissolved in that clear solution after digestion. If the solution is not clear, it has a little bit of brown or black, digestion is incomplete. You have to continue the digestion until all of the black, brown color, yellow color gone. That means all of your other organic matter has become fume. Oops. What? Yeah. All right. So the next step is a combination of neutralization and distillation. So I just pointed as distillation because the neutralization is part of this entire step that we call distillation. So what happens is we add NaOH, a concentrated solution of sodium hydroxide. So it's neutralizing the acid, but also reacting with our ammonium sulfate. So the NaOH is neutralizing the acid and reacting with the ammonium sulfate. So we always want to put excess NaOH to make sure that we neutralize and react. Once we have a reaction, we're going to get an ammonia. Ammonia is a gas. So because it's distillation, ammonia and water will evaporate, and then they will go into a condenser and they will be distilled into a boric acid solution. That where we titrate with HCl. So what happens here is that your ammonia reacts with boric acid to give ammonium borate. So now I fixed my ammonia that is in a gaseous state. It goes down with the water into boric acid and reacts with borate ion to give you ammonium borate. So now ammonium borate is a basic solution. I titrate with acid, usually HCl, and at equilibrium, the last drop of the acid will change the color. So I put an indicator, a methyl red indicator. It is methyl red, right? Yeah. So put methyl red indicator. It is in acid solution, it's red. Gives you red color. When we titrate and ammonium react with ammonium borate, it turns yellow. Basic. So we titrate back with acid until the last drop at neutralization. Another drop of acid will turn the color pink, and then we stop titration. So what basically happening here, if you notice, 1 mole of ammonia gas reacting with 1 mole of boric acid to give you 1 mole of ammonium borate. And then 1 mole of borate reacting with 1 mole of hydrogen from the HCl will give you back 1 mole of boric acid. So it's all 1 mole to 1 mole. So at equilibrium, 1 mole of my HCl is equal to 1 mole of ammonia. So 1 mole of nitrogen. By knowing the volume and the molarity of my acid, I can calculate the percent nitrogen, and I'll walk you through the calculation in a little bit. So what we use here is the equilibrium, and that 1 mole of amine group or nitrogen is equal 1 mole of the acid. And that's at equilibrium, we can derive the equation. And we will derive the equation in a little bit. Did I lose you anywhere? Okay. So here's a visual. So we will have a digestion block where we put the tubes that have your sample and concentrated H2SO4 and the catalyst. So we'll put the samples in these tubes, and then we bring it down, and then we heat the block. And this is connected to an exhaust system. So all the fumes will go into an exhaust system, get neutralized, and water will get collected. Acid that got condensed will get collected. So at the end, you'll have ammonium sulfate in a clear solution that will look blue. So here's your clear solution in blue. That is a distillation unit. So once we get that tube with your clear solution, we take it to the distillation unit. Here on the receiving end, we put boric acid with methyl red. It doesn't look like that, it looks red. Okay, it looks more like red. Okay, so and then here in the back, which you don't see in this picture, you will have water for steam generation to heat up. You will have NOH container. Then we dispense NOH here in the tube. And then what happens, we turn on the steam, and then everything starts boiling, and then water and ammonia will evaporate, goes into a condenser, and condenses into the boric acid. And then red starts turning yellow because it's becoming basic. And then we titrate with HCl to a last drop that will give you very light pink. It won't be that dark. You need to stop titration at the first hint of pink. Oh, this is just demonstrating that the ammonia and water goes into the boric acid, and it gets trapped with the boric acid, converting to ammonium borate. All right, so here is my story coming up. In my master's, 2 years almost, all I did is analyze protein and gluten fractions. It was torture because I just fractionate the gluten out of the wheat flour and then determine protein in my fractions, and I had a very old Cal-Val unit. So this exactly looks like that. So the digestion happened on these very old blocks, and then these big flasks. And this is the exhaust system that would suck up all of the fumes. And the top here is the distillation unit, where after gets completely digested, you put the water and then NOH, and you put it up and heat, and you have water running to distill into. In the back, you will have all your flasks that will collect the ammonia and water. So one time, my lab was on the first floor, and on the second floor was the unit. So I was, like always, filling all of the spots and digesting my sample. My samples. So I go up, and I don't see anything but a white cloud in the hallway. Oh my gosh, it's all the toxic fumes, white cloud. And then for my fear and shock, I see a head on top of the clouds. A very tall professor was walking down the hallway, and I can see only the head and then white fume. And he saw me and started yelling at me, "What did you do? We're being poisoned here." And then I was scared to death. And then I walked into the lab, and I saw that the exhaust system was switched off. I didn't turn it on when I was So luckily I was not fired. I was able to finish my digestion and graduate at some point. Yeah, but the poor guy was so upset that he was sniffing all the fumes in his office. Anyway, but lucky for you, you have a better system in the lab. Okay, so the last step is the titration, like I said. So you have the ammonium borate, the yellow color, and you titrate to the last drop at equilibrium would turn everything pink. Then let's derive the equation that you will be using to get percent nitrogen. So here's the derivation, but I'm going to walk you through it step by step. This equilibrium equation, we will be using it a lot for different things from now on to the end of the semester. So I will explain what happens. So what I want you to see those last important chemical reactions. So you have the ammonia reacts with boric acid, gives you ammonium borate. The borate ion or salt will react with acid to bring back boric acid. But as you can see, like I said, all is 1-to-1 molar ratio. So at equilibrium then, 1 mole of nitrogen equals 1 mole of what? HCl. Thank you. So 1 mole of nitrogen equals 1 mole of HCl at equilibrium. Right? When we reach equilibrium and the next drop turns pink, that means we are at this stage. So number of moles of nitrogen equals number of moles of HCl. So you will be given the standardized normality or molarity of HCl, which will be close to 1.1 molar or normal, molarity equals normality because we have 1 hydrogen. Okay, so it will be close to 0.1. We will be given the exact standardized molarity. So number of moles of HCl equal molarity times volume in liter. And then molarity is moles per liter. It's always good to put the unit because the units will cancel and then you will know that you're doing the right thing. All right, so for HCl, we have the molarity and then we will have the titration volume because the volume would be, once we reach the pink color, we stop and we read the volume. So you have the molarity of HCl and you have the volume. Now the volume will be in milliliters. So what do I need to do here? So I need to keep the unit in liter. So the volume, if it's in milliliter, what do? I divide by, how do I convert liters to milliliters? Divide by 1,000. So this way, the unit will be liter for me, so that I can cancel. So milliliter of 1,000 is liter, so I can cancel the liter units here. Because in your titration burette, you will be reading the volume in milliliter, not liters, obviously. So, but for the equation, you have to convert to liters. So you divide by it. Okay, are you following this side? Emma can't see the board, but but you guys can help Emma read it. So you're following up to here. All right, now let's look at this side. When I want to get percentage of nitrogen, I want to get grams per 100 grams of sample. That's the percent. So Do you remember number of moles equal what? And it's already here on the slide. It's mass over molecular weight. So now, because I want the mass, right? I want percentage. So I'll go, okay, mass of my nitrogen in grams over the molecular weight of nitrogen, and the unit is grams per mole. Are you following? I substituted number of moles by mass of nitrogen. This is my unknown. This is my X I'm solving. Over molecular weight of nitrogen, which is units grams per mole. Are we following still? What did you say? What's the X? Is the mass of nitrogen. This is what I'm looking for. I'm looking at how much nitrogen I have in my sample, right? Okay, so mass in grams of nitrogen, this is my X, so that I want to solve for. And then molecular weight of nitrogen is 14. 14 grams per mole is the molecular weight of nitrogen. So this is known. All right. So I'm solving for mass, so I can say that mass of nitrogen in grams of my nitrogen, I will bring the molecular weight of nitrogen over here. It will be then times 14 grams per mole. Are you following? Right? So instead of being here in the denominator, I moved it to the other side of the equations, and then it will be multiplied here. We're good? All right, so now this is mass. If I want to get a percentage of nitrogen in my sample, how do I do that? So this is the weight. If I want to get percent nitrogen, what do I do? Which is percent is mass, or instead of just mass, it's just gram of nitrogen. Let me be very clear. Grams of nitrogen in 100 grams of sample. That is my percentage. So what do I need to do for this equation? If I want to get grams per 100 grams, what I need to add here? Is we multiply that by 100? We multiply by 100 and divide by, it's grams per 100 grams of mass. Mass of the sample, the weight of the sample, yes. So I would just put everything here, the molarity in moles per liter, times volume in milliliter, times 14 grams per mole, over weight in grams of sample. And your 1,000, you don't want to forget that. Milliliter of 1,000 will give me the unit of a liter. And everything is times 100. So I can get percent nitrogen. So look at your unit. So I have mole here, cancels mole here. I have the milliliter by 1,000 cancels the liter. So now my percent is in gram per 100 grams. Very important to cancel liter so that you understand the derivation. Is there any place where you would like me to? Good? It's okay if you want me to repeat. Yes, take that picture, send to Emma. All right. If you're all good, I can proceed. All right. Now, take a piece of paper for a +2 and let's solve. Let's do some calculations that you will need for the lab. Take a moment, maybe 2 to 5 minutes. and calculate each rep separately, then average the rep. Can I erase this? And because we need to explain the rest of the equations. Are we good? You've got what you need?
Yeah, actually, yes. How are you so mean?
What did she do to me?
They started singing a song, so I said, "Who sings that?" And she said, "I don't know." I said, "You should do that that way." Since they call me evil. No, because you. I'm just trying to concentrate on calculating the Mexican.
Okay, yeah, you're being distracted. Okay. So one thing to get you going is if the protein, oh sorry, if the nitrogen content is 17.5, what would be your conversion factor? The equation is a couple of slides. 6.25? Wait, 6.25 is correct when percent nitrogen is 16. But in beans specifically, they have more basic amino acids. So the percent nitrogen in bean protein is higher than 16. It's 17.5. So what would be your conversion factor? How do you calculate your conversion factor?
100 divided by 17.5.
Correct. So 100 divided by 17.5 is equal
5.71.
5.71 is your conversion factor. Again, bean protein has more basic amino acid than your average protein. So you have higher percentage of nitrogen. That's why the conversion factor is lower, because the denominator is high. Okay. In cheese, for example, cheddar cheese group, you will find that your conversion factor is 6.38, which is higher than 6.25 because cheese has less basic amino acid than average protein. Start by just on wet bases before you do dry weight bases. What's that? Data is in wet bases, yeah. And another thing I forgot to mention, we always run a blank because sometimes your reagents might be contaminated by nitrogen. So we always run a blank. So usually your volume in the equation is volume of the sample minus volume of the blank. I missed telling you. Are you stuck anyway? So you really you don't have to work your way through the derivation of the equation. Just apply the equation. You have everything you need. Remember the volume, you subtract the volume of the blank. That's the only thing I forgot to mention earlier. And once you get the percent nitrogen, you multiply it by the conversion factor to get the protein. Only William didn't want to be out today. He sat where he really said. Yeah, you noticed that everybody else would pick me, but you didn't. Anybody with one first application? You have an answer?
I think percent nitrogen.
Yeah, what's the percent nitrogen per sample?
Or beta.
Correct. That's for sample 1. What is it? 3.48, correct. And now what do you have to do? Exactly. You multiply both by 5.71. So you multiply each by 5.71. What do you get? Did anybody go that far? What's that?
6.
Very good. Okay. So who is stuck? Who got stuck? Or you got stuck for a little bit? You got stuck for a little bit? Where did you get stuck? It's fine. Tell me. No, thank you, you said. You have nothing? Okay. So what's the molarity, Golden? What's the molarity?
Of SCL. 0.1142.
Very good. What's the volume? Minus?
Minus 0.6.
Very good. Molecular weight is there. What's the weight of the sample?
Do we have to convert it to dry?
Not yet.
Not yet. Okay.
You do that as the last step
Okay.
after we get the protein count.
So 1.015.
Yes, and then you have divided by 1,000 times 100, you get the percent nitrogen. Good?
Yeah.
And after you get percent nitrogen, you multiply by 5.71 to get the protein count. And that's, we do the same for rep 1 and rep 2. And you get 19.62 for rep 1. That's the percent protein, and then 19.87 for rep 2. That's the percent protein. And then you take the average of that, you add the 2 and divide by 2. What do you get for average? 19.74, yes. And then what? Now you calculate based on dry bases. On the final answer, you calculate on dry bases. And how do we calculate on dry bases? Do you remember? So we have 19.7, I'm gonna say, grams of protein in 100 grams of sample that is as is or wet. What is the dry matter? How much is the dry matter? What's the moisture content? 8. So what's the dry matter? 100 minus? Yes. So then I want to determine the percentage on only in the dry matter. So that would be, so I have 19.7 over 100. Oh, sorry, no. I have. Okay, so I need to determine the ratio of the protein on a dry matter, which is 100 minus 8 times 100. Okay, so I want my ratio of the protein to the dry matter times 100. So it's 19.7 grams relative to the dry matter times 100. What would it be? Wait a second. Oh, it's a dehydrated. I messed you up. Sorry. A dehydrated means a dried sample already. Yeah. All right, Pam. Thank you very much for confusing everybody. Okay. Yeah, if it was on wet basis, you could, but it's already a dried sample. No, then it would be relative to the wet sample, so it would be 19.7 grams in 100 grams times 100 minus 8. All right, so now what do you think? Oh, Emma texted, I can see it. You can see the board? What? Okay.
It's kind of like sheer. I can't see it all the way though.
I see.
But Marie sent me a photo, so it's okay.
Okay. Oh, let me see. I could have done this from the beginning. All right. So what did you get, Marie? Or you didn't get? Yes. All right. Okay. So time's up. We can talk about Dumas method on Monday. Yeah, go ahead.
So it's the first part we did on dry basis and then, okay.
Yes, because I forgot that the question says dehydrated. The timing is right already for
I guess we could have, we threw you off with our seats, you threw us off with the draft, wet and traffic.
I know.
We deserve that. He thanked us right back.
Thank you. Dividing the blame is always good. All right. Well, have a great weekend, and I look forward to seeing some of you in College Bowl. I have scones as treats.
Hope you did a nice Friday.
All right.
I have a question about the lab report.
Yeah.
Should I talk to, I don't know what TA is there. I think Andresa was there.